In this tutorial, you'll learn how to graph piecewise functions. Let's take a look at the most common functions that you'll be asked to graph in Algebra 1. There's linears, quadratics, exponentials, square roots, absolute values, and maybe even a cubic here or there. So you might be used to graphing functions, maybe even two functions on the same coordinate plane, where you enter the functions into your graphing calculator, into the y equals button. Then maybe you look at the table of values and you graph both of them on the same grid. Okay, so this is a system, and what you're often doing is looking to see where their points of intersections are, right? If I graph on my calculator here the second graph, which happens to be linear, x plus 1, and I actually look at the graph, I can see that I have a full quadratic function and a full linear function. They actually have two intersecting values here, or two solutions. But what we're going to work on today is maybe not graphing the whole curve, maybe not graphing the whole straight line. We're going to practice just graphing pieces. So let's talk about a piecewise function. A piecewise function is a hybrid function, and it's made up of different rules for different intervals. Remember, an interval is a section of your graph. So let's say we're looking at the section from x is equal to 2 and lower. That would be this way, right? X is equal to 2 and lower. It looks like this section of the graph is a quadratic. But if I look from x equals 2 and higher, which is this direction, it looks like this section of the graph is linear. And it looks like when x is equal to 2, I've got a lot of different things going on, right? So those are separate pieces of different functions. And the three functions that we're graphing here are x squared, 6, and 10 minus x. So our entire graph is a function called f. And that function follows three different rules depending on what the inputs are. So my first function is y equals x squared, my second function is y equals 6, and my third function is y equals 10 minus x. But because I have all three, I'm going to change this letter y to f of x. And so my function's name is f, and its input is the letter x. So each piece of our function applies to a different part of the domain. So if I put the number -1 into my function, it's going to follow this rule. It's going to get squared because it's a number less than 2. So if I put into my function a -1, it's going to be squared because it follows this first rule. If I put the number 4 into my function, do you know which rule it would follow? The first, the second, or the third? So if my input is 4, that would be this third rule because it's a value in input between 2 and 6. So if I input a 4 into my function, it's going to be 10 minus x, or 10 minus 4. So that's what a piecewise function does. It accepts different rules for different inputs. So let's get started. When you create your tables, you might want to create one large table instead of 3 separate tables, but it's entirely up to you. So because my first rule required inputs of a number less than 2, we included all of these values. -2, -1, 0, and 1. Then my middle rule here required an input that was exactly 2, so we made sure to include that in the table. And then our last rule was anything that was higher than 2 but less than or equal to 6. So we included all of these values. Let's take a look at this first graph and see if we can start making sense of intervals, or sections of the graph that contain different parts. So it looks like we have a function named f, and it follows two different rules. If you are a number lower than 1, we're going to take the absolute value of that number. Now, if you have some common sense understanding, you know that an absolute value graph has a V shape, right? It has a V shape to it. The second rule of our function is that if you are a value that is equal to 1 or even greater than 1, that you're going to follow the square root function. And if you have any recollection of that, it looks like this. All right, so let's see if we can understand which section of our graph is going to have that V shape. So again, on your number line, go to the number x is equal to 1. That would be here, and here, and here, and here. And what you're trying to do is look at the direction that's less than that. So we're looking this way, right? So we're looking this way. So let's use some common sense. Of all 4 graphs, which one has that V-shaped absolute value function? Well, it's definitely not this one, and it's definitely not that one. So I haven't even finished the problem, but I've been able to eliminate 2 choices already. All right, the second part, which is go back to x is equal to 1, but then look towards the right, which is greater than 1, which one has that square root function shape? That's right, this one right here. So that's why it's good to have a general understanding of the shapes of all those functions I showed you at the beginning. All right, how about this one? A function is graphed on the set of axes below. So which of those functions, f of x, are related to this graph? Well, we can definitely use some multiple choice strategies here. If you notice, the first rule of the function is exactly the same for all 4 choices. They all say x squared, and they all say for when the input is less than 1. Since all of them are the same, we probably don't even need to assess this part of the question, since it must be true, since all of them have it. All right, let's take a look at those second rules. They all have x's to the power of 1, so that must mean that they're all linear, which is good, because what I'm looking at is linear. And you'll notice something here, which I haven't mentioned yet. You'll notice that that is an open circle. And an open circle happens when you have one of those inequalities. And a closed circle happens when you have one of these inequalities. So it looks like my domain can start at the number 1, but it cannot be equal to it, which would make sense as to why all of these say that it has to be greater than the number 1. So that's why that open circle is there. So that makes total sense. All right, let's see if we can't start eliminating some choices here. So I can't really tell what the y-intercepts are because my linear function doesn't cross the y-axis, but I'm betting if it did, it would be around there, right? That's a good estimate. It's a good estimate for where it would be. So I'm kind of predicting that this will be wrong and this will be wrong. Maybe even this one, just by the fact that it doesn't look like it crosses below the origin, right? So let's double check this one. The other thing besides the y-intercept you can check is the slope. So I see a nice corner point here, a nice corner point here, a nice corner point here. Looks like it has a slope of up 1 over 2, up 1 over 2, up 1 over 2. And the only one that has that slope is choice number 2. Which makes sense because it follows along also with that y-intercept value that I predicted that this linear function would have had we extended that line. All right, so now that we've made sense of some of these piecewise functions, why don't we try graphing one? All right, let's take a look. Here's a piecewise function called f of x. The first rule is that I will take 1 minus the input as long as the input is less than or equal to 1. The second rule is I'll square the input and subtract 4 as long as the input is between 1 and 3. And the third rule is that no matter what you put in, it's going to come out as a 2. And that's for any number that is greater than or equal to 3. Now I know this part gives some kids a little bit of trouble. And that's because the rule says that the number has to be greater than 1, so students think that they can't put a 1 into the function. And that's absolutely not true. The reason why we are going to put a 1 into the function is because if you think it has to be greater than 1 and you put in the number 2, then what happens to all the numbers that are in between 1 and 2? What happens to the number 1.000000001? That's greater than 1, so it's a legitimate input. So you don't want to skip to the next integer. You don't want to say, oh, I can't use a 1 because it's not equal to 1. So what you want to do is put a 1 into the function, but when you go to graph it, make sure your point is an open circle. All right, so just because you can't be equal to 1 does not mean that you don't enter it into that function rule. You use it, you just don't graph it as a solid point. You graph it as an open point. All right, so how do we start our table? So I'm looking at my interval sections here, right? I can be something that's lower than 1, I can be something between 1 and 3, and I can also be something greater than 3. So I want to make sure that I am putting numbers in, right? I'm choosing a domain that does satisfy all 3 of these, right? I want to have some type of input for all 3. So as I'm thinking of possibilities, I'm going to start with a number that's lower than 1. So maybe I'll pick something like -2. Maybe I'll pick a 0. And then I'm definitely going to pick that number, which is 1. My next interval has to have a number 1 and a number 3, and it could even have something in between those. So I'm going to stick with integer inputs, right? I'm going to stick with my domain having integer values only because it's helpful, less complicated to graph. And now this one says I can be 3, which I already have in my table, but I also want to pick something greater than 3. So maybe I'll pick a 4 and a 5. All right, here we go. I'm going to put the number -2 into my function, and if I do that, it can only follow this rule. So when I put that -2 into my function, I'm going to do 1 minus -2. So I can do all that math myself, but I definitely don't want to make silly errors for no good reason. So what I'm going to do is I'm going to turn on my graphing calculator, I'm going to go to my y equals button, clear out any old work that I have, and I'm going to enter these 3 functions. So 1 minus x is my first function, x squared minus 4 is my second function, and 2 is my third function. Now when I go to look at my table of values, I'm going to scan all the way up to -2, and again, that can only go into my first function. So the output would be 3, and notice that I'm going to write it only in the output for that function. My next input is 0. Again, it can only go into my first function. So if I go down to input of 0, out will come a 1. And now for my next input, +1. So +1 definitely can go into my first function, and it comes out as a 0. But if I put it into my second function, which I am allowed to do because the boundary is 1, I can put that 1 into my second function. So if you look on my graphing calculator here, the output will be -3. However, this gets an open circle, and that one gets a closed circle. All right, so my next input is going to be 2, and 2 cannot be put into my first function. So I'm going to put it into my middle function, x squared minus 4. It comes out as a 0. The next input is 3, which is going to come out as a 5. Oops, sorry. I wanted to keep the color the same. 2 comes out as a 0, 3 comes out as a 5, but 3 can also be an input for my third function. And my third function says it always comes out as a 2, no matter what. Now I'm not going to look at the graph on my graphing calculator because my graphing calculator is going to show me the entire function, not just the pieces I'm interested in graphing. So now I'm going to start graphing my first piece of the function, which would be -2, +3, 0, 1, 1, 0. And this is a linear function, so I know that I'm going to have a straight line here. Now, this point, I remind myself, can be shaded in. This other points here, can actually keep going. I actually can have a number lower, so I'm going to put an arrow there. But I cannot put an arrow on this side because it must stop once I hit +1. Now my second graph, I'll put in blue. I have a 1, -3, and remember this one cannot be equal to 1, so I leave that value open. 2, 0, which will be solid, and 3, 5, which will also be solid. And no, actually, 3 is not included. So this one is going to be an open circle as well. And this one is a quadratic. This one is a quadratic. So if possible, I'm going to try and want to curve it a little. You see how I kind of didn't make that perfectly straight? Now the only reason I knew to do that was because of my common sense about what type of function that was. Now, if you made it perfectly straight, you would be wrong. So be careful when you're plotting your graphs. All right, the last part has a greater than or equal to sign, which means my first plotted point is going to be solid. So I plug in a 3, out comes a 2, and this is a 2, and this is a 2. And it can be any number greater than 3, so this is also going to get an arrow. And that is how you graph piecewise functions. All right, let's try one more. So for this function, I have inputs that range from -3 to 1, and then from 1 to 8. So if you'd like, you can actually make 2 separate function tables if that makes you more comfortable, as opposed to trying to figure it out with them both combined. So if you have a restricted interval, like we do here, note that your first value always has to be this number. Now, sometimes you have a solid circle, sometimes you have an open circle, but your first input and your final input must be these 2 values. So even if you don't have an equal to sign, you must have those 2 values in your table. How many values you choose to put in between there is up to you. Depends on how specific you want your graph to be. Obviously, the more points you put on your table, the more accurate your graph will be. So I know this is going to be a perfect V shape because I have some common sense about absolute value bars. So I'm going to kind of skip over here. Maybe I don't need to plot every single point. So maybe I'll put a -2, maybe I'll put a, I guess I can put them all since I have that many spaces in my table. Okay, so if I put in a 3, out's going to come a 3, out's a 2, out comes a 1, out comes a 0, out comes a 1. And the same is true for my blue function over here. I'm going to put in values from 1 to 8. Maybe I'll put a 2, a 4, and a 5. But I must start at 1 and I must end at 8. Noting that my beginning and my end values are actually included, so both of my points are going to be solid. But in my other graph here, my absolute value graph, my first value was included, which is solid, but my last value was not included, so that one's going to be open. Now you don't have to take those notes, but me writing them down hopefully will help you to understand how to graph. So my first absolute value graph, -3, 1, 2, 3, -2, 2, 1, 1, 0, and then 1, 1. So I have this part. Again, no arrows because I am restricted to this interval only. Now for my blue graph, this function is pretty simple. No matter what you put in, it's going to come out as a 4. So this one is very simple for me. You put in a 1, out comes a 4. Put in a 2, out comes a 4. 3, 4, 5, 6, 7, 8, it doesn't matter. But notice that I get only 1 arrow. Oops, no arrows, right? I can only go to 8. So I have no arrows here. So this will be your piecewise function. All right, let me show you one last thing. Sometimes you have functions that look like this. They're called step functions. And it has a constant value for a certain given interval. And then it moves up to the next value, and then it moves up to the next value, and the next value. And that's why you'll notice that you have these solid circles on top of these open circles. That's very important. Now you may not see these graphs in everyday life, but they're used quite a bit. Something I think that it's used mostly for are like parking meters, maybe even like wrestling tournaments. And those are situations where once you reach a certain time, or like in wrestling, once you reach a certain weight, you have to go up to a different class. And in parking meters, once you hit a certain amount of time, you have to go up to another cost value. Maybe it's $1 per hour. So as soon as you hit 61 minutes, you go up into the $2 range. As soon as as soon as you hit 121 minutes, you go up into the $3 range, etc. So here's an example of a test question. Morgan can start wrestling at age 5 in Division 1. He remains in that division until his next odd birthday, when he's required to move up to the next division level. Which graph correctly represents this information? So let's see. He can wrestle in Division 1 while he's 5, and then he moves up to the next on his odd birthday. So when he's 6, he stays in Division 1, but then as soon as he hits 7, he goes from one division up to the other division. You see that? The number 7 is going to have 2 points, because when you're 6.99999 years old, you are still in Division 1. But once you hit 7, you move up to the next interval. So let's take a look. This one has a closed circle at 5, and these two have open circles at 5. So he can be in that division at 5, so that means he needs an open circle. So these two are out. Now, as soon as he turns 7 years old, he can no longer be in Division 1. He must move up into Division 2. And that's what this graph is showing. He no longer is in Division 1. He's moved up into Division 2. This graph shows him being eligible to be in both divisions, and that's not allowed. So those are examples of piecewise functions and step functions, how to graph them, and how to interpret them.